To carry on the discussion of how we actually convey uncertainty whenever we're using a sample statistic to estimate a population parameter, we're going to think a bit more in this video about constructing confidence intervals. So in the previous video, we did some of the theory behind how we understand a confidence interval as a probability statement about a range over which we believe the true value of the parameter lies based on our sample information. And now we're just going to see how, in practice, with a set of data, one sample, we can construct that confidence interval, in particular how we can do that using regression techniques. We'll use Excel as our tool for that. So the most common parameter that you might want to be constructing a confidence interval for is the mean and of a population. So you estimate the mean of that population with the sample mean, and then with a couple of formulas you then can calculate the confidence interval. Now the approach that we take to that is to make use of regression, and we're going to show this in terms of Excel, but any kind of regression thing could produce the same result, that allows you to easily get the confidence interval for the mean, and later on you'll see the confidence interval for other parameters as well. So how do we do it? Well, we have to kind of trick regression functions just a little bit because they're not designed. Normally regression is designed for a case where you've got a y and an x, and the x varies over a whole range of different values and the y varies over a range of different values, and we're sort of basically putting a line through a scatter plot. In this case, we've got, as per this snapshot here, we've got y, the wage of the person, for example, depending over a range of different values, and the x, we're actually going to make all of the values of the x variable the same. They're going to be all equal to 1. And we can do that pretty easily in a spreadsheet program like Excel. We can just type in a 1 a couple of times and then drag that down, and so then we get a big long column of 1s. And then we go to whatever software we've got, Excel or otherwise, and do a regression. The column A in this case would be the dependent variable, the y variable, and column B would be the independent variable. We have to tick the box in Excel that says that we've got no constant, so constant is 0, because implicitly this column here actually is the constant, so we've made the constant equal to x. So once we've done that, we end up with regression output like this. And I think those of you who enrolled in the course and doing your workshop and homework would have actually done this in reality, and you would have calculated the average of a column of numbers, and then you would have also run that regression I've just described there and seen that the value that you get for the coefficient on that variable called mean is the average. So the mean of this sample of data is $33,161. And the reason we calculate the average this way rather than just going equals average is that the benefit of this is that automatically, as an additional piece of output with the regression, is the confidence interval that we're actually interested in. So this tells us these are the lower and upper bounds of our 95% confidence interval. So this tells us we are 95% sure that the mean wage of this population, which is a bunch of young people in the USA, is between $32,131 and $34,192. And we estimate the mean to be $33,161. So in a simple way, we've been able to communicate to people that we're trying to explain the results to that we have some degree of uncertainty in our estimation of the mean. That we don't really know exactly what the average wage is, but we're pretty sure that it's somewhere between 32,000 and 34,000, thereabouts. Okay, so that's as simple as that to construct the confidence interval for the mean. We can actually look at the different components of the formula just to check how this came about. And if you recall the formula from the previous video, it basically involves taking the sample mean that you got, subtracting the lower confidence half, and then adding the same quantity to give you that range. So you'll notice in the example that we've got here that the 33,161 is exactly halfway between the lower and upper confidence intervals. So it's x bar plus or minus a certain amount of there, and the certain amount that you take plus or minus of is this thing here. So S is the standard error, and if I take you back to the previous slide there, the standard error is 36,001. N is the number of observations, that's 4,692. And then the t value is the value of the t distribution that you would get from, if you're using Excel, using the t-in function, with a 5% range and degrees of freedom equal to 4, 6, 9, 1, which is n minus 1. This is the two-sided t distribution because we're doing a confidence interval in both directions. So we want 5% probability of being outside these values of t in either the upper or the lower direction. So 2.5% in the upper direction, 2.5% in the lower direction. So that's, if you go to the function wizard in Excel and ask it to explain the tin.2t function, it would tell you that's what you do. If you want basically 95% range, you want 5% outside that, and these are your degrees of freedom n minus 1, then this is what you type in, and it gives you 1.96. So if we take 33161 minus 1.96 times s, which was 36001, on square root of n, then we'll get exactly the answer that we want, and the range that we get is between 32,000 and 34,000 here. So there you go, you can check that for yourself and see how that particular formula is used. So obviously you never have to really do that in practice. Excel will just spit out those answers for you straight away. But notice, again, just to emphasize, what are the quantities that make a difference to your level of confidence? So for example, suppose I had a bigger sample size, I had more data in my sample, then I'm going to be dividing by a bigger number here, which means divide by a bigger number means this interval, this component of the interval will be smaller. So I will be more accurate with my estimate. My interval will be narrower because I've got more data. And similarly, some of the other components, each of these components, if I have, let's think a bit about S, for example, here. S is the standard deviation of the original data. So if the data itself is very spread out, then the estimation of the mean is going to be more difficult because the data is all over the place, so therefore you estimating the mean of that data is a tougher task. So the bigger S is, then the harder task you've got estimating the mean, so the more conservative you've got to be with your interval. So you've got to have a wider interval. Just, that might sound a bit the wrong way around, but just think for a moment. Suppose, for example, you're forecasting what the temperature is going to be tomorrow. Well, that's a relatively easy task to do. So if you could say it's going to be 26 degrees, and I'm pretty sure I have it right, so my interval can be quite narrow. It's going to be 26, but it might be between 25 and 27. Pretty sure it's going to be between 25 and 27. But if you want to forecast the temperature in 2 weeks' time, then you might still estimate it. It could on average be 26, but you really have not much idea about what possible temperature it's going to be, so your interval is going to have to be much wider. So less certainty, more difficult task, wider interval. So if your data itself is more spread out, it's more difficult to predict, then your interval has to be wider to compensate for that difficulty. Okay, so by looking at the formula, you do get some insight. Whilst we can just use a spreadsheet regression like this to just get the confidence interval, knowing the formula and knowing the components of it actually helps you get some insight into why sometimes you can estimate with great certainty, with great accuracy, and other times not so much. We could also just change in the dialog box the level of confidence. So instead of doing 95%, we could choose 99% or 90%, and that will change the interval. And once again, thinking about it a little bit, if I want to be 99% sure about something, I'm going to have to make my interval a little bit wider. You can do that for yourself in Excel if you want. Just change the 95 to 99%. 95 is the default. And you're now almost 100% sure, 99% sure at least, that the true mean lies between here and here. So to get that extra certainty, you need the interval to be a little bit wider. So that's what you'd find if you test that out. Okay, so that's confidence interval for the mean and some of the intuition and some of the logic behind confidence interval and how you actually do it in practice in Excel. Now, I've just chosen the mean because it's the most commonly estimated quantity that you calculate with a sample, but there are other things that you're interested in. For example, you might be interested in estimating the correlation between X and Y, two variables. That's extremely important in data analytics. We're spending most of our time in data analytics trying to find patterns in data, and we find one of the key components of patterns in data is to actually see that this variable and this variable tend to work in the same direction. When one goes up, the other goes up, or when one goes up, the other goes down, etc. So correlation is a very important quantity. We spend a lot of time thinking about it. Here's the formula that we have for calculating the correlation. It's a bit of a pain in the neck to plug that in and calculate it, and even worse to calculate the confidence interval for it. But the good news is that with a bit of creativity, which we don't expect you to be able to prove this to be true, but take my word for it, if I create a variable, which is y minus its mean divided by the standard deviation, and another variable x minus its mean divided by the standard deviation, and I regress y star on x star, then the coefficient that I get here, with an intercept by the way, is equal to the correlation coefficient between these two variables, the estimated correlation coefficient. Okay, so all I have to do is imagine if I was doing this in Excel, take my original data, y, which is in one column, and next to it perhaps is the x data, use equals average to calculate the mean, equals standard deviation, stdev.s, to calculate the standard deviation for y and for x, and then use a formula to take each y value, subtract the mean, divide by the standard deviation. So I've now got a column. I originally had a column of y and x, now I've got another column which is y star and x star. And I do my regression of the y star, column C or whatever it is, on the x star, column D. When I do that, here's my correlation coefficient, and here's my confidence interval for the correlation coefficient. So we're 95% sure that the true confidence interval for the population is somewhere between 28% and 30.8% and 34.3%. So our sample estimate is 31.5%, and that's reasonably accurate because you're pretty sure that the true value is somewhere between here and here. Okay, so it's that easy for us to construct a confidence interval for the correlation. Another quantity that you're often interested in is confidence intervals for proportions. So you've got a set of data and you want to know what proportion of your sample is employed, for example, and you want to look at that for the difference between females and males. How do you do that? Well, we set up a regression as follows. I think you may have seen this regression in the previous section, but now what you can imagine is we've got the you've got a column of values which indicates whether the person is employed or not, and in the next column along you've got whether they're male or female. So 1 if they're female and 0 if they're not. So you estimate that regression of y on x. Strange looking regression, but it's fine to do it, no problem. And the coefficients of the intercept and of the female variables tell you something about the proportions. This is the same as what was in the previous video, so if you want to go back and review that, then it's you're welcome to do so. So the coefficient of the intercept is the value that would apply if this variable was equal to 0. So if this is equal to 0, then you're not a female, which means, assuming that we only assume to a binary classification here, then the person would be a male. So we've got a 0.75 chance of a male being employed, because the dependent variable here is equal to a 1 if they're employed and 0 if they're not. So 75% of the sample of males are employed. So my estimate of the population parameter, which is the percentage of males who are employed, is 0.75. If I want to estimate the percentage of females who are employed, then this coefficient here tells me it becomes relevant when this dummy variable is equal to 1. So if you've got a female, then the probability that they're going to be employed is equal to 0.75 minus 0.41666. The 0.75 always applies because it's the coefficient of the intercept, which applies for everybody. So 0.75 minus 0.41666 gives me 0.333 or 0.33. So this tells us that 33% of my sample of females were employed. So my estimate of the population parameter, the proportion of employed females, is 0.33. Okay, so that's pretty interesting, isn't it? A dramatic difference between the employment rate of males and females in this case. Now, if I wanted confidence intervals for those, it'd be easy for me to get a confidence interval for the proportion of males who are employed. That just comes straight from over here. And I see it's somewhere between 0.16 and 1.33. Whoa, that's pretty amazing. That says, whilst my estimate of the population proportion of employment is 0.75 for males, I'm actually extremely uncertain about that estimate. It's not at all accurate. The true proportion could be somewhere between 16% and 133% with 95% confidence. That's a huge range of data, of uncertainty. Why is it so uncertain? Well, it's uncertain because don't forget I've only got 10 data points here. So I've got 10 people, some males and some females, some employed, some not, and based on just 10 people, I'm estimating two quantities of interest. What proportion of the males are unemployed, or employed rather, and what proportion of the females are employed? Well, not surprisingly, I'm going to get a pretty inaccurate estimate with just 10 data points. So that's reflected in the fact that my confidence interval for the proportion of males who are employed is extremely wide. Now, it's actually a little tricky for me to get a confidence interval for the proportion of females who are employed because I don't have one number for that. The proportion of females employed is this number plus this number, which is 0.75 minus 0.41, giving me 0.33. So in fact, easiest thing for me to do would just be to find a new variable which is equal to 1 if you're a male and 0 if you're a female, and then look at the coefficient of the intercept in that case, because that would be the coefficient of female. That would give it to me straight away, but I haven't done that here, but that would be the simplest way of doing it. That's what this suggests. But let's just go back for a sec and have a look at what confidence interval we did get, which is the confidence interval for the proportion of males who are employed. Notice it goes from as low as 0.16 up to 1.33. Hang on, proportions have to be between 0 and 1. How can I have a proportion of 1.33? 133% of males. There are more employed males than there are males. Can't possibly be true. And that's exactly correct. There's nothing incorrect about the calculations here. This is the confidence interval as calculated using the method we've given to you, but there's nothing in the way we've set things up here to prevent that strange result from happening. It's going to happen in this case because there's such a poor amount of information, such a very broad confidence interval. It just happens to be that it gives us a confidence interval which is completely implausible. So there's nothing wrong with what we've done. It's just that we've ended up with a result that actually doesn't make a lot of sense in this case. And you just got to be a little bit alert to that possibility. So probably you'd actually say, look, in fact, it can't be bigger than 1. So my confidence interval actually goes from 0.166 up to 1. But to be honest, you would never use results like this in any meaningful sense of the word because it's such a lousy estimate. You don't waste your time giving information to anybody based on a sample of just 10 people. But you get the idea. It's just illustrating some of the challenges that you face in practice sometimes. Okay, so the purpose of this little video was just to show you how in practice, relatively easily using the same kind of general approach, with a simple regression of a y and an x, I can estimate a confidence interval for the mean, for the correlation coefficient, and for proportions of, in two different categories here, proportions of males, proportions of females. So very easy to get those things and easily to understand the confidence interval in each case. Okay, thanks very much.